How you doing? In this video, I'm going to continue the discussion on quantum nonlinear optics by solving for the second order polarization and susceptibility. In the majority of this video, we're going to solve for the second order expected dipole moment, d superscript 2, which from the previous video we saw was a sum like such. So the majority of this video, I'm going to be finding this quantity explicitly. So from the last video, we also have the knowledge of what the bra and the kets of psi 0 look like. So we know that. We know this. We know this one. And we know the form of this one. And now we see that, well, in the second order perturbed dipole moment, we need to find the bra and ket of psi 2. So, to start off, I'm going to do that. Okay, so that's the form of psi 2, the ket side of psi 2. And going from here to here, all I did was plug in CB of 2, which was also found in a previous video. And so if you need to refer to those, you can look at those movies, but I like to have them written down in front of me. For instance, here's all my notes for the first video, and here is where I have the expression that we started with right there, and I also have the perturbed coefficients right here, so it's all laid out in front of me. I don't remember all this stuff. I usually have it written down in about 10 places. Okay, so now that we have that, I should also mention, okay, so going from here to here, I also canceled these exponents with omega b in the exponent. And you can do this because the way I defined omega bg is basically e to the I omega b times e to the minus I omega b. So those are going to just give you 1. So that's why I didn't write it here. Okay, and now we will write the bra side of psi 2. Okay, so that's our bra side of psi 2, and forgive me, I keep forgetting to write the denominator, but it is there if I look at my previous expression for the second order perturbed coefficient. There's a denominator there. I'm just forgetting to write it. Okay, and also in this bra side, so there's both of these terms here, complex conjugates, and I switched the subscripts because note that there is a rule. I'm pretty sure this is a thing. I have yet to prove it to myself, but I wrote mu ag times ei naught star. I just distributed the star this is true. I have proved this one to myself. But it's the next part which I have not proved to myself. But I'm pretty sure this is correct. So mu Ag star equals, so it's the expectation value of the dipole between states G and A. But it's the complex conjugate, and you can just flip the bra and the ket when you take the complex conjugate. So it'd be like this, which that's just equal to mu GA. So that's what I did going from this line to this line. Okay, so now I'm going to solve for each of the terms up here individually. And the first one I'm going to do is the first term. Okay, so I'm calling this one here the first term, this one here the second term, this one here the third term. So, first term is psi 1 mu psi 1. And I have psi 1 from the previous video, which is just, here it is. I'm just showing this to prove. I have it right here. So that's what I'm using. Oh, and this term is a little bit weird, and I'll explain more at the end, but we're going to sum over all the basis states, and we're going to have the indices. So, okay, here's my notes from the previous video. I said the ket of psi 1 is summed over all basis states A and all frequencies I, but I did the same thing with the ket. But these are just dummy indices, so you can change the letter to whatever you want. But the bra and the ket are going to have different indices in what I write to follow. And I don't know precisely why that's the case. And I don't know why they're not just the same. So I'm sorry I can't explain that. But it's something to do with, you gotta have, if you have an element in some basis state in the ket, you have to sort of take into account that basis state with all the basis states of I. So I hope that's a satisfactory explanation. Probably not, but that's how it's done. Okay, so let's get into it. Okay, so now here, remember what I just said. So this is this thing in square brackets here is the ket side of psi 1, but I'm summing over different basis states B and different frequencies J. Okay, so that's our final form for the first term. Sorry I couldn't write everything over here, but this is just the electric field at frequency J. So Ej naught e to the I omega sub j times t. So one term down, two to go. Now we will solve for the second term. Okay, so that's our final form for the second term. And notice, I rewrote the matrix elements such as this. I just rewrote mu AB. So this thing here is actually the same thing here. I know, even though they're different terms, it just means the same thing. So for instance here, the mu GA is just equal to the psi basis state G mu psi basis state A. Okay, now for the final third term. Oh, I just realized I made a mistake up here in the second term with the denominator. So the second term here should be minus omega I minus omega j. Minus omega I minus omega j. Okay. Okay, there we go. There's a final form for the third term. Now, I'm sort of manipulating the exponents, so I hope you're following that. For example, here we have e to the I omega gt. Here we have e to the minus I omega gt. So I canceled those, and I also wrote e to the negative I omega I minus omega jt. I put those into two terms, and that's what you see there. But I think you're probably following that part. Okay, so now we have all three terms, and I'm going to write out in full the second order perturbed dipole moment. So I'm going to sum all these, and then I'm going to try to put it in a nice symmetric looking form, and then we'll talk about the second order polarization and susceptibility. So summing all the three terms on the previous page together, we get the following. Okay, so that is just the sum of all the three terms on the previous page. And now I'm going to sort of rewrite things to make things look a little bit simpler. So I'm going to rewrite the electric fields, since there's the part at time 0 times the time dependence part. I'm just going to rewrite that as one term. So in other words, if we take e to the I naught e to the negative I omega I t, I'm now going to just rewrite that as e sub I. And also note in this, it's important to realize you're summing over all positive and negative frequencies. And that essentially, negative and positive frequencies I and j. And that essentially lets you choose whether you want to put a plus or minus there. Because you're really doing both of them when you sum over all the frequencies. So I'll be changing a couple of these denominators, the minus signs, a couple of them I'm going to be changing to plus. Okay, so yeah, now let me do that just to clean things up a tad bit. Okay, there we go. So there's our final, I don't want to say clean, but the cleanest way we can make it for the second order dipole expectation value. And I tried to rearrange the transition dipole moments to sort of notice that, okay, this index ends in A, but the beginning index here is A. This index is B, the beginning index here is B. So this sort of gives us a link between all this math that we're writing and the physics of the situation. So if you ever see a Feynman diagram, a double-sided Feynman diagram, where one side represents Bra and one side represents Ket, this sort of gives you an idea of how to draw the Feynman diagram for the specific process that's happening in that term. Or in other words, you can do an energy level diagram. So if you have ground state G here, you have excited state A here, excited state B here. Well then, mu GA represents going from G to A, mu AB represents going from A to B, mu BG represents going from B to G. So that's sort of how you would draw the energy level diagram for the process that's happening in this term. So that's why I organized it in that manner. And there's also links between how I wrote this here and all the second order nonlinear processes, some frequency generation, second harmonic generation, difference frequency generation, and that other one, which I cannot think of the name right now. It's the one where there's just a static electric field. But that is all related to this. And, I mean, in general, the second order polarization. So, for the second order polarization, all we do is multiply this d2 by the number density. Just like we did for the first order polarization. So, number density d is the number of dipoles divided by the volume times d2. So that's, whoops, I wrote a 1 there. This should be a 2. So the second order nonlinear polarization is just that. And to get the second order susceptibility, we do it in a similar manner to how we did it for the first order susceptibility. We remember the equation that says we can write the polarization in the k direction, the second order perturbed polarization in the k direction, is equal to some constant, epsilon naught, sum over all I and j, and then you have the susceptibility here. You have the I, j, k element of the second order susceptibility times each of the electric fields. And so you can relate this expression to how this looks, and from that you can find all the elements of the second order susceptibility tensor. And there's also some more things that we could speak about in this video, but I will not get into them, partly because I do not understand them that well, and partly just out of pure laziness. So sorry about that. And these topics I'm talking about are the reality of the fields, intrinsic permutation symmetry, and symmetries for lossless media. I won't be going into any of that. And if you see a different form for this second order susceptibility or polarization, and it looks different, it might look different, but that's because of these properties relates them all. Okay, well, I hope you found that helpful. Thanks for watching. Have a great day.